Hi there. I am inside of a Jupyter notebook over here, and I'm about to share some results of some experiments that I ran that are kind of meant to fool you. Let me first explain what I did. There is this dataset out there that is called the credit card dataset. You can find it on many blogs as well as Kaggle, but the whole point is that this dataset has lots of different values that you are interested in using to predict whether or not there was fraud. So you can imagine I've got this matrix X with lots of floating point numbers, and I've got my target variable Y in an array. And one theme of this dataset is that we are dealing with a class imbalance. So far, so good. But what I'm now going to do is I'm going to be running a random forest to see if I can get a good fit. What I'm also going to do is I'm going to cross-validate my results, which basically means that both of these two datasets get split into train and test sets multiple times. But when I do that, what I get out is some sort of a score. I'm going to be taking the F1 measure for the score here, but the metric itself is not necessarily the important bit. The important bit for this video is trying to figure out whether or not we are able to do hyperparameter search for this random forest in a way that we're able to make the model better by reflecting on some metrics. And that's also what this chart over here represents, by the way. You see, what I've done is I've instantiated a random forest with some hyperparams, and I ran this in such a way that it's not just one set of hyperparameters that goes in. I have set number 1, set number 2, set number 3, etc., such that I'm trying out 1,000 different combinations of hyperparameters over here. And what this chart over here depicts is all these different values as time moves forward as I'm trying out different hyperparameters. And this red line over here represents the best score that I have found so far. And when I look at the results, and when I zoom in a bit, it does seem to be the case that as I'm trying out all these different hyperparameters, I do actually get kind of lucky quite early. Right around the 200 mark over here, a little bit before, I see that I get a very high value. And as I zoom out, you can also quite clearly see that I don't get a higher value for a while. In fact, that's the highest value in the entire set. I can also look at this picture slightly differently, though. And that is what I'm doing in this histogram over here. Instead of showing all these different runs over time, I just turn them into a histogram. And you can see that there are lots of different values that have been evaluated. And you could look at this and you could say, well, we found one combination of hyperparameters here that is the best. After all, it has the highest score. Not only that, we can also see that there's actually quite a bit of margin over here. There's a substantial difference from the best performance to the worst one. But here is where we might be able to fool ourselves. When you make a chart that looks like this, and when you then inspect your hyperparameters and then say, well, let's take the model of this hyperparameter set over here because that obviously has the best score, do we then have the best model? Or can we, by accident, fool ourselves if we do this? And it turns out in this case, yes, you can. Now I'm being a little bit cheeky here because I didn't actually show you the code that resulted in this histogram. But I'm going to show you a small snippet now. In short, my code has this experiment function that is going to run lots and lots of times, and inside of that goes an integer. And this integer is going to determine what hyperparameters I'm going to be trying out over here. In this particular case, though, I am not doing anything sensible with the hyperparameters. The only hyperparameter that I'm setting is the setting for the random state. So that means that in all of my experiments, I'm not really doing hyperparameter search. I'm just changing the random state of this random forest classifier. And although it might be counterintuitive, this chart does demonstrate that just by changing this, we can have a substantial difference. If I go from the smallest to the highest number, that is definitely a margin well above 10% in difference. And that implies that we should be kind of careful. If we have a machine learning algorithm that has a little bit of noise in it, well, then if we run a large grid for hyperparameter tuning, then it might just be that we see a very high score in the end due to noise. And this phenomenon actually has a name. This is the optimizers curse. It's a very subtle phenomenon, but it can bite you. And in fact, in the rest of the video, I kind of want to show you how easy it is to maybe get bitten by this. And just to demonstrate this, you might wonder, well, what would happen if we just simply didn't do this? What would happen if we didn't have a different seed value every time that we run such an experiment? Would you then expect that these results become a whole lot more consistent? Well, here's what that would actually look like. I'm no longer manually setting the random seed over here, but you can still see that we get a very wide distribution. In fact, the difference that we see over here is pretty much the same as above. Sure, the histogram shape might be slightly different, but by and large, it does feel like we're still drawing from a very similar distribution over here. The reason here is very, very subtle, and it kind of has to do with how you run this experiment. The random state, by its default, is equal to none. And in theory, that means that you're just going to get random state from the machine that you're running on, not necessarily something that is going to be consistent. If you really wanted to get consistent results here, what you would have to do is you would have to add random state equal to a set number over here. There's a small culture around the number 42, so you could go ahead and do that. But in general, if you want consistency, it really helps to set this value. Only when all the hyperparameters here are set, and if there is a random state over here, then and only then have I gotten the same score out from the system. But whenever there's an opportunity for a random forest classifier to introduce noise to the system, I've consistently gotten a distribution that goes out from all these different scores. And if you know how a random forest works, that also makes sense. The name random is in the name of the estimator. There is a lot of noise in this system, and that's also how this estimator functions. However, there's a little bit more that meets the eye to this one in particular. So what I'm going to do now is I'm basically going to redo this chart, but for an experiment that has been altered. In this case, I'm setting the random seed. I'm also setting the max depth. I'm using the mod operator over here to make sure that I get some different values. And I'm also going to be using this number that goes in to keep on increasing the number of estimators over here. The thinking here is that this should be somewhat consistent. We have a random seed that's set, and I'm going to be trying out lots of different combinations between the max depth and the number of estimators. So, does this completely remove the cursive optimality? Well, at a first glance, we can see that the histogram that goes out is a lot different. You can actually kind of see that there are these clusters of distributions, so to say. It's not one normal distribution over here. So that does imply a big change. If I squint my eyes a little bit, I also think we get a higher score than what we did before. We seem to be around a 0.8 over here, and if I just quickly scroll back up, the highest we got over here was 0.75. So that definitely feels like we're doing a bunch better, especially because the smallest value over here is also a lot larger. So that's nice. But to really understand what's happening here, we should stop making these histogram charts and we should actually go a bit deeper. In particular, what we're going to look at now is the effect of the number of estimators and the max depth on this score over here. And that's something I've done in the two charts over here. This chart over here shows the number of estimators and the relationship with the score, and this chart over here does the same thing, but with the maximum depth. Now note that these are scatter charts, so there's lots of dots being drawn over each other over here. But one thing I can see when I just squint my eyes a bit is that there do seem to be 3 levels, and those are mainly defined by the hyperparameters over here. Having a higher maximum depth seems to have a positive impact. And if I squint my eyes further, I think that also translates to the chart over here. If I look at what numbers score well in the max depth, and if I were to sort of relate that to what I see on the left, then it definitely feels like the number of estimators over here, it doesn't really have that much of an effect. It really seems to be determined by the max depth over here. Now, it deserves to be emphasized in this video that I am cherry picking a little bit. I picked an algorithm here that's highly susceptible to the optimizer's curse, and you can definitely argue that I could have gone for more sensible hyperparameters in this demo. However, with that caveat out of the way, I do think that there is an important, albeit subtle lesson that we can learn here. In practice, it is not just the random state that is causing the optimizer's curse to take place. Instead of random state, you might also be dealing with hyperparameters that in the end don't really matter. When I look at this chart, I really get the impression that the number of estimators doesn't really matter much at this point. But there is still a bit of wiggle room when I look at the max depth and when I look at the best score that it has. It's not so much noise in the sense that there's a random number generator or anything like that happening, but there's still a little bit of noise because there's a hyperparameter that's changing things a little bit, but mostly in a way that just introduces noise. And that means that you don't need the random state to have this optimiser's curse to worry about. That said, I do think that there are a few quick lessons to learn here. Even though the optimizer's curse is something to always keep in the back of your mind, it is not something that you don't have any remedies for. One thing we saw is that it is a good practice to just use the random state whenever you're interested in doing an experiment formally, mainly just because it removes a whole lot of noise from the system. Second of all, we also noticed that visualization is still good. It's one thing to claim a high score, but it's another thing to also understand the relationship between the score and the hyperparameters. And this is an exercise we probably shouldn't skip. That said, the main lesson of the optimizer's curse is to just be slightly careful if you're going to be doing big grid search, so to say. If you are going to be dealing with lots and lots of hyperparams, then just the fact that you're running the experiment many times, that might be causing a perceived uplift, when in reality you should always just be a little bit critical.